What if everything you know, every moment, every memory, the very fabric of existence, could vanish in an instant? Picture the cosmos, vast and eternal, its countless stars burning bright against the infinite dark. Now imagine that darkness swallowing everything, not just space but time itself. No past, no future, just nothing. It's a thought so unsettling, so unimaginable, that it feels like the plot of a science fiction epic. But what if it's not fiction at all? What if the end of time isn't just a dramatic idea, but a real possibility lurking in the equations of physics, hidden in the mysteries of the universe? This is the terrifying, thrilling frontier we're about to explore together. From the heat death of the universe to the bizarre quantum theories that suggest time might just stop, scientists have proposed dozens of ways our reality could meet its ultimate expiration date. Some are slow, almost poetic, a gradual fading into silence. Others are violent, catastrophic, over in the blink of an eye. And then there are the theories so strange, so counterintuitive, they'll make you question everything you thought you knew about existence itself. Today, we're diving into 30 of the most mind-bending theories about the end of time. We'll unravel cosmic mysteries, grapple with the ideas that keep physicists awake at night, and maybe, just maybe, come face to face with the ultimate fate of everything. Whether you're a science enthusiast, a casual stargazer, or someone who just loves a good existential rabbit hole, this journey is for you. So settle in, open your mind, and let's ask the unthinkable together. What happens when time runs out? Let's start with one of the most haunting possibilities, the Big Crunch. Imagine the universe not as an ever-expanding frontier, but as a cosmic rubber band stretched to its limit before snapping back with unimaginable force. This theory suggests that gravity, the same force that holds us to the ground and keeps planets in orbit, could one day overpower everything. Right now, the universe is expanding, galaxies drifting farther apart like dots on an inflating balloon. But what if that expansion isn't eternal? Scientists have theorized that if there's enough matter in the cosmos, enough gravitational pull, the universe could eventually slow its expansion, stop, and then reverse. Galaxies would start rushing toward one another, space itself shrinking like a deflating tire. Stars, planets, even the fabric of reality would be pulled inward faster and faster until everything collides in a single catastrophic moment. All matter, all energy compressed into an infinitely dense point, a mirror image of the Big Bang. And just like that, time itself would cease. No more ticking clocks, no more cosmic history, just an unfathomable singularity where physics as we know it breaks down completely. What makes this idea especially chilling is how it flips our understanding of existence on its head. We think of time as a river always flowing forward. But in the Big Crunch scenario, that river doesn't just dry up, it flows backward, erasing the universe's story as it goes. Entropy, the natural tendency toward disorder, would reverse too. Broken teacups might reassemble, scattered ashes returning to unburned logs. Of course, no one would be around to witness this eerie rewind. Long before the final collapse, conditions would become so extreme that life, even atoms themselves, would be torn apart. Some physicists argue that a Big Crunch could even trigger another Big Bang, a cyclical rebirth where the universe starts anew, but for us, for everything we've ever known. It would be the definitive end, no second chances, no remnants, just silence, as if existence had never been at all. But what if the universe isn't destined for a dramatic collapse? What if, instead of a fiery reunion, everything just drifts apart forever? To understand why some scientists still take the Big Crunch seriously, we have to look at the clues hidden in the oldest light in the cosmos, the cosmic microwave background. This faint glow, left over from the universe's infancy, is like a fingerprint of creation, and it holds secrets about how much stuff is actually out there pulling everything together. For decades, astronomers assumed there was enough matter, enough gravity, to eventually halt the expansion. But then came the plot twist no one saw coming: dark energy. In the late 1990s, observations of distant supernova revealed something shocking. The universe isn't just expanding, it's accelerating. Some mysterious force, nicknamed dark energy, seems to be pushing galaxies apart faster and faster. This discovery threw the Big Crunch theory into doubt. If dark energy keeps winning the cosmic tug-of-war, gravity won't stand a chance. The universe might never reverse course. Instead, we could be headed for a very different fate: the Big Freeze. Picture this: trillions of years from now, every star burns out, every black hole evaporates, and the cosmos becomes a vast, dark, icy graveyard where even atoms decay into nothingness. Time would still tick forward, but with no change, no events, it might as well stop. Yet the debate isn't settled. Some models suggest dark energy's strength could change over time. What if it weakens or flips from repulsive to attractive? Suddenly, the Big Crunch is back on the table. Then there's the curvature of the universe itself. If space is closed like a sphere, it could eventually contract, but measurements of the cosmic microwave background so far suggest a flat universe, one that could expand indefinitely. The truth is, we're still piecing together the puzzle, and every new telescope, every deeper look into the void, brings us closer to answering the ultimate question. Will the universe end with a bang, a whisper, or something even stranger we haven't dreamed of yet? Now let's step into the silent, creeping doom of the Big Freeze, a fate so gradual it makes the fiery collapse of the Big Crunch seem almost merciful. Picture a universe where expansion never stops, where galaxies grow so distant from one another that their light can no longer bridge the gaps. Over trillions of years, stars exhaust their fuel one by one like dying embers in a campfire. Eventually, even the most stubborn red dwarfs, those faint, long-lived stars, flicker out. Space becomes a graveyard of black holes and the frozen remnants of planets, so far apart that no future civilization, if any could survive, would ever know another existed. This is the heat death of the universe, where entropy, the slow unraveling of order into chaos, reaches its maximum. Every chemical reaction, every exchange of energy relies on differences in heat and pressure. But in this frozen future, everything evens out. No more hot stars, no cold voids, just a uniform, lukewarm nothingness. The cosmos becomes a static, featureless expanse where nothing happens. Time, as we understand it, loses all meaning. Without change, without events, does time even exist? And then comes the real kicker. Even the building blocks of matter itself might not last. Protons, those indestructible anchors of atoms, could decay. If certain theories hold true, over mind-boggling timescales like 10 to the power of 34 years, protons themselves might dissolve into radiation. Atoms, the foundation of everything we see and touch, would simply evaporate. Black holes, the last surviving structures, wouldn't escape either. Through a process called Hawking radiation, they'd slowly leak energy, growing smaller and hotter until they vanish in a final, silent pop. When the last black hole winks out, the universe will be a sea of stray particles and radiation, stretched so thin that temperatures approach absolute zero. No new stars will ignite, no planets will form, no life, no thought, no light, just an endless frozen stillness where the very concept of time becomes meaningless. There's no clock ticking in an empty void, no past, no future, just an unchanging, eternal present. And yet, in this bleak scenario, the universe doesn't so much end as fade into irrelevance. Existence continues, but in a form so alien, so devoid of activity, that it might as well not be there at all. What's haunting isn't just the idea of cold and darkness, it's the erasure of meaning itself. Every story, every discovery, every act of courage or love, reduced to a faint whisper in a cosmos that no longer remembers how to listen. But here's the twist. Some theories suggest even this frozen eternity might not be the final chapter. Quantum fluctuations could, over incomprehensible timescales, spark new Big Bang's pockets of rebirth in the cosmic graveyard. Whether that offers comfort or deeper dread, though, is up to you to decide. But what if the universe after heat death isn't quite as empty as it seems? Imagine floating in that infinite void where even atoms have decayed into whispers of energy. No light, no warmth, no movement, just an endless sea of near-perfect stillness. It's a grim picture, but some theories suggest there might still be flickers of something. Strange, fleeting moments where the universe, against all odds, conjures up the impossible. Take Boltzmann brains, for instance. Named after the 19th century physicist Ludwig Boltzmann, this bizarre idea proposes that in a universe stuck in maximum entropy, random quantum fluctuations could, given enough time, spontaneously assemble a fully formed conscious mind. Not a brain attached to a body, not a person with memories or a past, but a solitary, self-aware moment floating in the dark. A mind that pops into existence, experiences a single disorienting thought, "Why am I here?" and then vanishes just as quickly. The math, in a twisted way, checks out. In an infinite timeline, even the most improbable events become inevitable. Given enough time, particles could randomly arrange themselves into any configuration, including a working brain. But here's the unsettling part. If Boltzmann brains are possible, how do we know we aren't them? Right now, you might feel like a continuous consciousness with a lifetime of memories, but statistically, a randomly assembled brain in a dead universe is far more likely than an orderly, evolved one like ours. The idea turns reality into a cosmic crapshoot, where existence itself might just be a fleeting glitch in the silence. And yet, there's another twist lurking in the quantum foam. Even in a frozen universe, tiny fluctuations could, over unimaginable eons, create pockets of order. Imagine a universe so vast and old that somewhere, somehow, quantum randomness sparks a new Big Bang. A fresh universe bubbling up from the ashes of the old, carrying no memory of what came before. If that's true, then heat death might not be the end, but a dormant phase, a cosmic hibernation before the next cycle begins. But what does that mean for consciousness? If a new universe emerges, will it birth new minds to ponder their own existence? Or is consciousness itself just a temporary phenomenon, doomed to fade with the stars? The chilling truth is, we might never know. In a universe destined for heat death, all meaning, all memory, all evidence of our existence will eventually dissolve into the void. And yet, there's something strangely poetic about that. If the cosmos can conjure minds from chaos, even briefly, then maybe existence, no matter how fleeting, is enough. Or maybe it's the universe's final joke, that in the end, even the deepest questions are just whispers in the dark, destined to go unanswered. The universe isn't just expanding, it could be racing toward its own violent dissolution. This is the nightmare scenario known as the Big Rip, where dark energy doesn't just push galaxies apart but grows stronger over time, eventually overwhelming every force that holds reality together. Picture this. First, the cosmic acceleration becomes so extreme that galaxy clusters can no longer cling to one another. Neighbors like Andromeda and the Milky Way, destined to collide in billions of years, would instead be wrenched apart as space itself stretches faster than light can bridge the gap. Stars within galaxies would next lose their gravitational tether, flung into the void like embers from a dying fire, but the terror doesn't stop there. As dark energies grip Titans, planetary systems would unravel. Imagine Earth's orbit around the Sun dissolving, our planet catapulted into the freezing darkness alone. Then comes the moment when even atomic bonds, the glue of matter itself, can no longer resist. Protons and electrons, separated by the exponential stretching of space, would be torn asunder. Mountains, oceans, even your own body would disintegrate into a cloud of particles, each isolated in an instant. Finally, space-time itself would fracture. The fabric of reality, shredded beyond repair, would leave behind a chaotic nothingness where not even the laws of physics hold sway. Timelines for this catastrophe vary, but some models suggest it could happen in as little as 22 billion years. That might sound distant, but cosmically, it's a blink, and here's the twist. If dark energy behaves as certain theories predict, this process wouldn't be a slow fade but a crescendo of destruction. The final milliseconds would see spacetime itself vibrating apart like a drumhead stretched until it snaps. Unlike the Big Crunch or heat death, the Big Rip offers no lingering silence or cosmic rebirth, just an abrupt total erasure of structure. What makes this theory so unsettling isn't just the scale of destruction, but the implications for time's arrow. In a universe where spacetime fractures, causality breaks down. No more before or after, no more history, just an infinite, fractured now where existence becomes a mosaic of disconnected moments, each isolated in the void. Yet for all its horror, the Big Rip remains speculative. Dark energy's true nature is still a mystery. Could it really grow infinitely stronger, or might it plateau or even fade? Until we know, this cosmic doomsday lingers at the edge of science, a shadow both terrifying and tantalizing. Phantom energy takes the horror of the Big Rip and cranks it up to nightmare levels. Unlike ordinary dark energy, which pushes the universe apart at a steady pace, phantom energy grows stronger over time, a runaway force with no off switch. The math behind it is as elegant as it is terrifying. If phantom energy exists, the expansion rate wouldn't just accelerate, it would approach infinity. Space itself would stretch faster and faster until even the fundamental forces holding atoms together are overpowered. Picture a rubber band stretched so violently that it doesn't just snap, it vaporizes. But how real is this doomsday scenario? Supernova surveys, which measure the universe's expansion by tracking the brightness of exploding stars, offer clues. So far, the data suggests dark energy's strength has remained roughly constant. Phantom energy, by contrast, would leave a different fingerprint, an exponential surge in expansion rates over cosmic time. Yet when scientists analyze ancient supernova, their light doesn't quite match phantom energy's ruthless predictions. The universe is accelerating, yes, but not that fast. At least not yet. Here's where things get speculative. Some theorists argue that phantom energy could still lurk in our future, its effects too subtle to detect today. Imagine a snowball rolling downhill, slowly at first, then unstoppable. If phantom energy's equation of state, a measure of its pressure and density, dips below a critical threshold, it could trigger an irreversible chain reaction. Galaxies would redden and vanish from view as their light stretches beyond detectable wavelengths. The cosmic microwave background, our window into the early universe, would fade into silence. And then the final act, spacetime itself ripping apart at the seams. Critics counter that phantom energy violates cherished physics principles like the conservation of energy. Others propose tweaked models where its effects plateau or reverse, a cosmic reprieve. But if observational data ever did point to phantom energy's existence, the implications would be staggering. We'd be staring down a countdown to oblivion, where the universe's expiration date isn't just inevitable but calculable. No heat death, no crunch, just a singular, violent moment when reality ceases to cohere. The debate hinges on a deeper mystery. What is dark energy really? Until we crack that enigma, phantom energy remains a spectral threat, a what-if lurking in the equations. But for now, the universe keeps its secrets, expanding at a pace that's unsettling but not yet apocalyptic. Whether that's comforting or ominous depends on how you feel about cosmic roulette. Now, let's venture into one of the most unsettling theories of all, one where the universe doesn't just end, but gets rewritten. Imagine physics itself as a set of rules scribbled in pencil, and suddenly, something comes along with an eraser. That's the nightmare scenario of vacuum decay. At its core, this idea hinges on a terrifying possibility. What if the laws of reality aren't as stable as we think? What if the universe is sitting in a fragile state, like a marble balanced on the edge of a hill, just waiting for the slightest nudge to roll into oblivion? Here's how it works. Quantum fields, the invisible forces that govern everything from light to matter, aren't always in their lowest energy state. Think of it like a frozen lake. On the surface, everything seems solid and unchanging, but beneath that ice there's liquid water, a lower energy state. If the ice cracks, the whole system collapses into it. Similarly, our universe might be trapped in a false vacuum, a temporary arrangement where the Higgs field, the thing that gives particles their mass, isn't at its most stable level. And if even a tiny patch of space were to quantum tunnel into the true vacuum, a bubble of destruction would erupt at the speed of light, rewriting physics as it expands. Inside that bubble, the rules we rely on would cease to exist. Atoms might not hold together. Gravity could invert. The very fabric of reality would unravel in ways our brains can't comprehend. And the scariest part, you'd never see it coming. The bubble would expand at light speed, giving no warning before it hits. One moment you're sipping coffee, the next you, and everything else are erased from existence, replaced by a new universe playing by alien rules. So how real is this threat? The Higgs field does seem suspiciously metastable, like a universe-sized ice cube that's slightly too warm. Particle colliders like the Large Hadron Collider have probed its behavior, and while the data isn't definitive, there's a slim chance we're living on borrowed time. Some physicists argue that if vacuum decay were possible, it would have happened already in the cosmos's 13.8 billion-year history. Others counter that it could be a ticking clock, with the odds increasing over time. But here's a twist. If a true vacuum bubble did form, it might not be doom for everyone. In an infinite multiverse, other regions of space could remain untouched, islands of stability in a sea of rewriting physics. That's cold comfort for us, though once the bubble starts, there's no stopping it. No escape, no survival, just a silent reboot of reality itself. And yet, in a bizarre way, vacuum decay isn't purely destructive. It could also be a cosmic reset button, birthing a new universe with entirely different laws. For us, it's the end. For some future, unknowable reality, it might just be the beginning. The chilling takeaway: our universe's laws might not be eternal. They could be a temporary arrangement, a fluke in an endless cycle of cosmic reinvention. And if that's true, then the only thing more fragile than existence itself is our understanding of it. Could humanity accidentally trigger the end of reality? It sounds like the plot of a sci-fi disaster movie, but Stephen Hawking himself once warned that our thirst for knowledge might carry existential risks, including the possibility of kickstarting vacuum decay. Picture a high-energy physics experiment, like those at the Large Hadron Collider, where particles are smashed together at nearly light speed to uncover the universe's deepest secrets. Most of the time, these collisions produce fleeting subatomic fireworks that teach us about quarks, neutrinos, even the Higgs boson. But what if, in some freak accident, they did something far worse? The nightmare scenario goes like this. Under extreme conditions, energies we've never achieved naturally on Earth, a particle collision could create a microscopic region where the Higgs field collapses into its true vacuum state. Think of it like poking a hole in the fabric of reality, a tiny puncture where the rules suddenly change. Once that bubble forms, it wouldn't just sit there. It would expand at light speed, rewriting physics in its wake. The shockwave wouldn't just destroy Earth or even our galaxy, it would erase the known universe as we understand it. Hawking raised this specter in his later writings, though he stressed the odds were astronomically low. After all, cosmic rays, high-energy particles from deep space, have been bombarding Earth for billions of years at energies far beyond anything our colliders can produce. If such collisions could trigger vacuum decay, it likely would have happened already somewhere in the cosmos, But here's the catch: our universe is vast and we've only observed a fraction of it. There could be regions where vacuum decay has happened, its lethal bubble still racing toward us at light speed, invisible until the instant it arrives. Critics argue this fear is overblown. The Higgs field seems stable enough based on current data, and even if a true vacuum bubble formed, some theories suggest it might not sustain itself like a spark fizzling out in wet grass. Others counter that stability isn't guaranteed. If undiscovered particles or dimensions exist, they could lower the energy barrier keeping the Higgs field in place, turning a safe experiment into a cosmic detonator. The debate boils down to a haunting question: how much risk is acceptable in the pursuit of knowledge? Particle accelerators operate under rigorous safety reviews, but the unknowns loom large. Some propose building detectors to scan for signs of vacuum decay in distant space, a cosmic early warning system. Yet even if we spotted a bubble, there'd be nothing to do but watch. No shelter, no escape, just the eerie certainty that physics itself is about to reboot. What makes vacuum decay uniquely terrifying isn't just the scale of destruction, but the helplessness it imposes. Unlike an asteroid impact or supervolcano, there's no survival strategy, no bunker deep enough. It's a reminder that existence might hang by a quantum thread, and that thread could snap at any moment without warning, rewriting the story of everything in an instant. What if the universe isn't a one-time event, but a cosmic heartbeat expanding and contracting in an endless loop of death and rebirth? This is the mesmerizing promise of the cyclic universe theory, where the Big Bang isn't the beginning, but just another turn in an infinite cycle. Picture a cosmic accordion breathing in and out over eons, each collapse birthing a new explosion, each explosion destined to collapse again. Time itself would reset with every cycle, like a clock striking midnight only to start fresh at dawn. One of the most compelling versions of this idea comes from brain cosmology, a spine-tingling offshoot of string theory. Imagine our universe as a three-dimensional brain, a membrane floating in a higher dimensional space, like a sheet of paper suspended in a vast, unseen ocean. Now picture another brain parallel to ours, invisible yet eerily close. According to this theory, every few trillion years, these brains could collide, unleashing energy so colossal it sparks a new Big Bang. The violence of that collision would erase all traces of the previous universe, resetting the cosmic calendar to zero. Stars, galaxies, even the laws of physics could emerge anew, unrecognizable from what came before. But there's another twist in this cosmic saga: Roger Penrose's conformal cyclic cosmology. Unlike the dramatic collisions of brain theory, Penrose's vision is eerily elegant. He proposes that as the universe approaches heat, death spread thin and cold. All matter eventually decays into massless particles like photons. At this point, the universe becomes so smooth and featureless that the very concept of scale loses meaning. A single photon could, in a way, span the entire cosmos. And here's the kicker: this ultra-smooth state becomes mathematically identical to the conditions of the Big Bang. Time and space effectively forget their own history, allowing the universe to cycle into a fresh beginning without any bang or crunch at all. What makes these theories so revolutionary is how they handle time's arrow. In most models, entropy always increases, creating an irreversible flow from order to chaos. But in a cyclic universe, entropy gets wiped clean with each reset. Imagine a deck of cards shuffled back into perfect order, or a shattered vase reassembling itself every cycle erases the damage of the last. Critics argue this violates thermodynamics, but proponents counter that the rules might simply reboot with each new universe. After all, if time itself resets, who's to say the old laws still apply? And then there's the haunting question: if the universe cycles endlessly, are we doomed to repeat the same story over and over? Or does each iteration spawn entirely new realities with different constants, different laws, maybe even different forms of life? Some models suggest information from past cycles might leave faint imprints, cosmic echoes in the microwave background, or patterns in black hole mergers. If we could decode those signals, we might glimpse universes that existed before our own. Yet for all its grandeur, the cyclic universe idea isn't without its flaws. The math is thorny, the evidence speculative, and the very notion of a resetting timeline strains intuition. But maybe that's the point. If the cosmos teaches us anything, it's that reality is stranger than fiction, and the true nature of time might be the strangest story of all. Hidden within the faint glow of the cosmic microwave background, some researchers believe they've found ghostly fingerprints of universes that existed before our own. Roger Penrose, the Nobel Prize-winning physicist behind conformal cyclic cosmology, points to peculiar anomalies in the CMB, tiny, circular patches where the temperature fluctuates more sharply than standard models predict. He calls them Hawking points, named after his late colleague Stephen Hawking, and claims they're the smoking gun of a cyclical universe. These points, Penrose argues, aren't random noise but the remnants of supermassive black holes from a previous cosmic cycle. They're evaporating energy imprinted like scars on the newborn universe's first light. The idea hinges on a breathtaking claim. When black holes vanish via Hawking radiation in the distant future, they don't just disappear, they leave behind bursts of energy that might echo into the next Big Bang. In Penrose's model, these echoes manifest as Hawking points, glowing slightly hotter or colder than their surroundings. His team analyzed CMB data from the Planck satellite, identifying dozens of these unexplained circles with unlikely statistical significance. If true, it would mean we're literally seeing through the veil of time, glimpsing the death throes of a universe long gone. But the scientific community remains deeply divided. Critics argue these alleged Hawking points could just be artifacts of data analysis, statistical flukes, or systematic errors in how we process the CMB's faint signal. Others point out that the standard cosmological model, which assumes a single, linear universe, already accounts for most temperature variations without invoking speculative cycles. The Planck collaboration itself hasn't endorsed Penrose's interpretation, cautioning that the anomalies could stem from mundane sources like interstellar dust or instrumental noise. Then there's the entropy problem. In a cyclic universe, entropy must reset with each new cycle, but thermodynamics insists it can only increase. Penrose counters that at the end of time, when all particles become massless and the universe stretches into featureless uniformity, the concept of entropy loses meaning. It's a radical solution, but one that leaves many physicists unconvinced. Yet for all the skepticism, the allure of Hawking points persists. Future CMB experiments with even finer resolution could settle the debate, either confirming these anomalies as cosmic relics or consigning them to the graveyard of intriguing but unproven ideas. Until then, they remain tantalizing enigmas, whispers from a past that might not even be ours. What if our universe isn't a three-dimensional reality, but a cosmic mirage, a hologram projected from some distant two-dimensional surface? The holographic principle, born from the study of black holes, suggests just that. It's a mind-bending idea. Everything we see, touch, and experience, from the swirling arms of galaxies to the neurons firing in your brain, might just be information painted on the edge of existence. But if the universe truly is a hologram, what happens when the projection fails? Could time itself glitch out like a corrupted video file flickering into static? At the heart of this theory lies the black hole information paradox. When matter falls into a black hole, it doesn't just vanish. According to quantum mechanics, information can't be destroyed. But where does it go? Nobel laureate Gerard T. Hooft and physicist Leonard Susskind proposed that the information isn't lost. It's smeared across the black hole's event horizon, the point of no return. Imagine throwing a book into a fire. The pages burn, but if you could somehow analyze every photon and wisp of smoke with infinite precision, you could reconstruct the text. Similarly, a black hole's surface might encode everything that falls inside, like a cosmic hard drive. Now stretch that idea to the entire universe. If the cosmos has a surface where all information is stored, a boundary far beyond our observable horizon, then reality as we know it could be a projection from that boundary. This isn't just philosophy, the math checks out. The holographic principle has become a cornerstone of quantum gravity research, bridging Einstein's relativity with the fuzzy rules of the quantum world. But here's where it gets eerie. All systems degrade, hard drives fail, codes corrupt. So what happens to the universe if its underlying data starts to erode? Some theorists suggest that quantum errors could accumulate over cosmic timescales, like cosmic rays flipping bits in a celestial computer. Tiny glitches might first appear as subtle violations of physics, particles popping in and out of existence where they shouldn't, or constants like the speed of light drifting unpredictably. Over eons, these errors could snowball, warping the fabric of reality until the projection unravels entirely. Time, dependent on the smooth flow of information, might stutter, skip, or simply stop like a film reel snapping mid-scene. The most terrifying possibility, we might not even notice. If the hologram's code corrupts from the outside, our three-dimensional reality could dissolve instantly without warning. One moment, existence hums along, the next, it winks out like a deleted simulation. There'd be no collapse, no explosion, just silence, as if the universe had never been. Yet there's a twist. If the holographic principle holds, death might not be final. In a pixelated universe, information is immortal. Even if our projection fails, the underlying data could persist, waiting to be rebooted in some future cosmic cycle. It's a strange comfort. The universe might not be a thing, but a story. And stories, even when interrupted, can always be retold. What if the universe isn't just governed by physics, but by lines of code? This is the spine-chilling premise of the simulation hypothesis, the idea that our reality might be an advanced digital construct, a cosmic video game run on some unfathomable computer. And if that's true, the most unsettling question isn't how it's done, but why. Why keep the simulation running, and what happens when the creators decide to pull the plug? Philosopher Nick Bostrom framed this dilemma in his famous trilemma. Either one, virtually all civilizations go extinct before reaching simulation-capable technology. Two, they choose not to create ancestor simulations. Or three, the haunting possibility, we're almost certainly living in one. The logic is cold and mathematical. If advanced civilizations do run simulations, the number of simulated minds would vastly outnumber real ones. Statistically, the odds tilt toward us being mere strings of code in someone else's experiment. But here's where it gets eerie. If we're in a simulation, its creators could terminate it at any moment. No warning, no countdown, just an abrupt shutdown, like a computer screen blinking to black. All of history, every triumph and tragedy, every whispered "I love you" and unanswered question erased in an instant. Time wouldn't just end, it would be deleted as if it never existed at all. Some theorists point to strange anomalies, glitches in reality itself, as potential clues. Take the Mandela effect, where large groups misremember events with eerie consistency. Did Nelson Mandela really die in prison in the 1980s, or was that a day to corruption in the cosmic server? What about déjà vu, those uncanny moments when life briefly stutters like a skipping record? Skeptics dismiss these as quirks of human memory, but what if they're artifacts of a simulation running on finite processing power? Then there's quantum mechanics, where particles seem to exist in multiple states until observed, as if the universe is optimizing resources by only rendering reality when someone's looking. Even the speed of light, the universe's ultimate speed limit, could be a hardware constraint preventing the simulation from overloading, the darkest twist. If this is a simulation, its purpose might be mundane. maybe we're an academic project for alien grad students or a forgotten background process in a vast digital ecosystem. And when the experiment concludes or the servers need maintenance, our entire universe could be archived or erased with a keystroke. Yet for all its horror, the simulation hypothesis offers a strange kind of hope. If reality is code, then deletion isn't necessarily the end. Backups might exist, data could be restored, the architects might even reboot the simulation, spawning a new universe with slight tweaks to the parameters. But for us, trapped in the runtime, there'd be no way to know until the lights go out. So the next time your phone glitches or déjà vu creeps in, ask yourself, was that just a brain hiccup or a flicker in the cosmic mainframe? And more importantly, who's watching the shutdown timer? If we're trapped in a simulation, why not try to break out? The idea of escaping our digital prison might sound like science fiction, but some theorists argue it's not just possible, it might be inevitable. Think of it like a video game glitch. Players find exploits all the time, clipping through walls or accessing hidden code. If our universe runs on rules, even unfathomably complex ones, there could be cracks in the system waiting to be discovered. One wild proposal involves manipulating quantum physics to rewrite the simulation's code. Quantum particles already behave like they're cheating reality, teleporting information instantaneously or existing in multiple states at once. If we could harness that strangeness, we might engineer a backdoor, a way to alter the program from within. Imagine tweaking the cosmic settings, changing gravity's strength or the speed of light, just to see what happens. The risks are terrifying, of course. One wrong move could corrupt the entire simulation, triggering an immediate shutdown. But for some, the gamble might be worth it. Then there's the dream of digital immortality. If consciousness is just data, why not upload our minds outside the simulation? Futurists like Ray Kurzweil speculate about mind uploading, where human brains are scanned and transferred to a more stable substrate, perhaps a higher-level reality supercomputer. Even if our universe gets deleted, our digitized selves could live on, free from the simulation's constraints. Skeptics point out a glaring flaw. If the outside world is just another layer of code, we'd be trading one prison for another. But the boldest idea, communication. If the simulators are watching, maybe we can send them a message. Physicists have toyed with embedding signals in particle collisions or manipulating cosmic rays to spell out patterns visible to higher dimensional observers. It's a cosmic SOS, a plea for answers or mercy. The chilling truth, though, is that any response might be catastrophic. What if our creators see our meddling as a virus and hit delete? Or worse, what if they're long gone, leaving us running on autopilot in an abandoned server? The most haunting possibility isn't that we're powerless, but that escape might be meaningless. If the simulation is all we've ever known, is there even an outside to reach? Or is the hunger for freedom just another line of code, a scripted rebellion to keep the experiment interesting? For now, the simulation hypothesis remains a paradox, a theory that could explain everything, yet offers no way to prove or escape it. All we can do is keep playing the game, searching for glitches in the system, and wondering if the programmers left us any clues. Envision a future where the cosmos isn't torn apart or frozen into silence, but slowly devoured from within. This is the fate of a universe ruled by black hole dominance, a timeline where gravity's relentless pull merges every galaxy, every star into an all-consuming darkness. Picture this: over trillions of years, galaxies collide and supermassive black holes at their centers spiral toward one another, locked in a dance of annihilation. With each merger, their event horizons swell, swallowing more of space until eventually, the universe becomes a single, monstrous singularity, a final black hole, so vast it could contain the entire history of existence within its shadow. But here's where time itself twists into the surreal. As this mega black hole grows, its gravitational grip warps the flow of time so drastically that the last moments of the universe stretch into an eerie eternity. Near the event horizon, time slows to a crawl, a phenomenon called extreme time dilation. From the perspective of a hypothetical observer falling in, the outside universe would appear to accelerate wildly. Billions of years would flash by in seconds as stars burn out, galaxies fade, and the cosmos empties. Meanwhile, for anyone watching from afar, the observer's descent would seem frozen, their final scream never quite reaching the void. Now consider the last photon. As the universe cools and expands, light becomes scarcer, stretched to whispers by cosmic inflation. Eventually, only a single photon might remain, drifting through the void, its wavelength so elongated it carries less energy than a thought. In this black hole-dominated era, that photon's journey would be a paradox. As it approaches the event horizon, time distorts so severely that, from the photon's perspective, crossing the threshold takes an infinite duration. It never quite arrives, yet from the outside the photon vanishes in an instant, the last flicker of the universe, swallowed without a sound. This scenario reveals a chilling truth about black hole endings. They're less about destruction and more about suspension. The singularity doesn't just crush matter, it traps the very concept of before and after. Inside, all events, every birth, every death, every cosmic dawn pile up at the edge of the horizon, frozen in time like insects in amber. The universe's story isn't erased, it's archived in a place where no one, not even light, can retrieve it. Yet there's a haunting beauty in this oblivion. Black hole dominance suggests that the cosmos might not end with a whimper or a bang, but with a silence so deep it echoes. And in that silence, time itself, once the river carrying all things, becomes just another prisoner of gravity's endless night. What if time isn't a one-way street, but a loop where the future becomes the past and the past becomes the future? This is the mind-bending premise of time reversal, a theory rooted in one of the most profound symmetries in physics, CPT invariance. At its core, this principle states that the laws of the universe should hold true if you flip three things simultaneously: charge, parity, and time. Swap every particle with its antimatter twin, mirror the universe like a reflection, and run the clock backward, and physics should still work the same. It's a dazzling idea, suggesting that time itself might be reversible at a fundamental level. But here's the paradox: if time could flow backward, why don't we remember tomorrow? Why does an egg splatter when it hits the floor but never leap back into your hand? The answer lies in entropy, the universe's stubborn tendency toward disorder. You can't unscramble an egg because scrambling increases entropy, and entropy only grows over time, or so we thought. Some theorists speculate that in an unimaginably distant future, entropy might peak and then spontaneously reverse. Picture a cosmic pendulum swinging back, with shattered teacups reassembling, scattered ashes coalescing into logs, and memories unfolding in reverse order. Critics pounce on this idea with a simple observation: if time reversal were possible, why don't we see any evidence of it now? The universe is relentlessly marching toward higher entropy, from the Big Bang's low entropy state to today's sprawling chaos. If entropy could just flip directions, we'd expect at least some regions of space to exhibit decreasing disorder. Yet every experiment, every observation, shows entropy rising like an unstoppable tide. Even black holes, the universe's ultimate entropy factories, only grow larger and more chaotic over time. But proponents counter with a tantalizing loophole: quantum mechanics. At microscopic scales, particles don't always play by entropy's rules. Quantum fluctuations can create order from disorder, if only fleetingly. In an infinite universe, given enough time, these fluctuations might cascade into a full-scale entropy reversal, a statistical fluke so vast it resets the arrow of time itself. The math allows for it, even if the odds are vanishingly small. The most haunting implication: if time reversed, consciousness might too. your final thought could become your first, your death, your birth. You'd experience life backward with no memory of the future because your brain would unravel as entropy rewound. It's a cosmic amnesia so complete you'd never know time had flipped at all. So is the universe a two-way street or a one-way slide into chaos? For now, the evidence favors the latter. But in a reality governed by quantum uncertainty, even the most immutable laws might just be waiting for the right fluctuation, a random roll of the dice that resets the clock and sends time spiraling backward into the unknown. Consider a universe so old, so vast, that even the impossible becomes inevitable. This is the eerie promise of Boltzmann's fluctuation, a theory where time itself could reboot through sheer random chance. The idea stems from Ludwig Boltzmann's 19th century insight. Given enough time, even the most improbable events must occur. In an infinite cosmos, particles jostling through emptiness could, by pure accident, arrange themselves into any configuration, including a momentary replica of our entire universe. Not a rebirth with galaxies and stars, but a fleeting bubble of order in an ocean of chaos. Now here's where it gets stranger. If randomness can conjure a universe, why not a single, self-aware mind? Enter the Boltzmann brain paradox. In a cosmos ruled by statistics, isolated consciousnesses' brains popping into existence complete with false memories of a past should vastly outnumber evolved beings like us. Statistically, you're far more likely to be a Boltzmann brain, a flicker of thought in the void, than a person with a real history. So why does reality feel so stable? Why aren't we all momentary hallucinations in an eternal dark? Critics pounce on this with razor logic. If Boltzmann fluctuations were common, we'd expect reality to glitch constantly, stars appearing and vanishing, laws of physics shifting on a whim. Instead, we observe a universe bizarrely fine-tuned for consistency. Supporters counter with cosmic inflation. Perhaps our universe is a rare fluctuation that inflated fast enough to stabilize, a statistical jackpot where order took root and stuck. But that raises another question. If time's arrow can reverse via fluctuation, why hasn't it happened yet? The answer might lie in entropy's stubborn grip. For a fluctuation to reset time, entropy would need to locally decrease so drastically that it effectively rewinds the cosmic clock. Quantum mechanics allows this in theory. But the odds are so vanishingly small that even in a Google years, it might never occur. Unless, and here's the twist, our universe isn't infinite. If space-time is finite, then Boltzmann's nightmare becomes avoidable. The cosmos might simply be too young, too small for such freaks of probability to manifest. Yet the paradox lingers like a ghost in the equations. If consciousness can emerge from chaos, how do we know we're not just phantoms of the void, destined to dissolve as swiftly as we formed? The chilling truth, we can't, but the very fact we're here debating it might be the best argument against it. A Boltzmann brain wouldn't ponder cosmology. It would blink in and out too fast to question its own existence. So maybe reality's persistence is the ultimate proof we're not just quantum accidents. Or maybe, just maybe, that's exactly what a Boltzmann brain would tell itself to keep the illusion alive. Across cultures and millennia, humanity has envisioned the end of time not as a cold equation of physics, but as an act of divine will, a moment when God steps in to halt the cosmic clock. Norse mythology paints Ragnarok as a cataclysmic battle where gods and monsters clash. The world drowns in fire and ice, and time itself fractures before rebirth. Christianity's Book of Revelation foretells a final judgment where heaven and earth flee from the throne of God, and time shall be no more. These aren't just stories, they're profound attempts to grapple with a terrifying question. If time began with creation, could it end with the Creator's command? Modern physics, strangely enough, doesn't outright dismiss the idea. Einstein's relativity shows that time is malleable. It slows near massive objects, speeds up in voids. If gravity can warp time, could an omnipotent force freeze it entirely? some theologians argue that a deity existing outside space-time wouldn't be bound by its rules. Picture a programmer pausing a simulation. From inside the code, everything simply stops mid-calculation. No decay, no collapse, just suspension. Skeptics counter that this conflates metaphor with mechanism. Divine intervention, by definition, violates scientific causality, making it untestable. But here's where it gets thorny. Quantum mechanics already allows for observer-dependent realities. If consciousness can influence quantum states, as some interpretations suggest, could a supreme consciousness observe the universe into stasis? The clash between these worldviews reveals a deeper tension. Science seeks explanations rooted in natural laws. Faith often transcends them, yet both grapple with time's fragility. Whether through Ragnarok's wildfire or a physicist's equations, we're left staring at the same abyss, wondering if time's flow is as inevitable as it feels, or if something or someone could silence the ticking with a word. Picture two soap bubbles drifting through an endless void, each containing its own universe with unique laws of physics. Now imagine them colliding not with a pop, but with a cataclysmic rewriting of reality itself. This is the spine-tingling scenario of false vacuum collision, where our universe could be annihilated by a rogue vacuum bubble from another realm, the trigger. A more stable universe, one where the Higgs field or other quantum properties exist at lower energy, expanding into ours at light speed, overwriting the very rules of existence as it goes. The idea emerges from cosmic inflation theory, which suggests our universe underwent exponential expansion in its earliest moments. But if inflation can happen once, why not elsewhere? Some multiverse models propose an eternal foam of bubble universes, each with different physical constants, endlessly budding off from one another. Normally, these bubbles remain isolated, their boundaries expanding too rapidly to ever touch. But if two bubbles form too close together, or if one bubble's wall slows just enough, impact becomes inevitable. What would that collision look like? First, we detect an anomaly in the cosmic microwave background, a bizarre temperature gradient or polarization pattern where the bubble wall made contact. Then physics would start glitching. Fundamental constants might shift unpredictably. Gravity could weaken, atoms lose cohesion, or light change speed. By the time we noticed the bubble's boundary, a wall of exotic energy thicker than galaxies would already be upon us, erasing our laws of physics like a virus corrupting a computer file. Stars wouldn't explode, they'd simply cease to function, their nuclear fusion processes rendered impossible under the new rules. Time, space, causality, all would reboot according to the invading bubble's logic. The terrifying beauty of this theory lies in its inevitability. If eternal inflation is real and bubble universes infinite, then statistically, a collision isn't just possible, it's guaranteed. We might be the new bubble, having overwritten some earlier universe without a trace. Or we might be next in line with a more stable vacuum's lethal wall already racing toward us at light speed, undetectable until it's too late. Yet here's the twist. Some physicists argue these collisions could be cosmic blessings. A bubble with weaker nuclear forces might prevent stars from ever forming, but one with tweaked dark energy could rescue civilizations from heat death. Our universe's fine-tuned constants might even be survivors of countless such collisions, each pruning away unstable configurations until only Goldilocks conditions remained. So is the cosmos a battlefield of colliding realities, where universes cannibalize each other in a silent war of physics? Or are we floating in peaceful isolation, our bubble forever expanding into the void? For now, the question hangs in the quantum foam just beyond the edge of our vision. What if death isn't the end, but just another path in an endless maze of realities? This is the unsettling premise of quantum immortality, a thought experiment where consciousness stubbornly persists through every possible timeline, no matter how improbable. The idea emerges from the many worlds interpretation of quantum mechanics, where every decision, every random event splits the universe into branching realities. In most branches, you live an ordinary life, but in some you die, or at least a version of you does. The twist, from your perspective, you'd only ever experience the timelines where you survive, no matter how unlikely. Fall off a skyscraper, in one branch you splatter on the pavement, but in another, a freak gust of wind nudges you onto a ledge. Your consciousness follows the path where you're still alive, again and again, like a ghost stepping through closing doors. Now take this logic to its cosmic extreme. If consciousness truly clings to existence, what happens when the universe itself begins to die? Imagine a future where stars burn out, black holes evaporate, and the cosmos drifts toward heat death. In most branches of reality, entropy wins, civilizations crumble, minds flicker out, and time itself becomes meaningless. But in a vanishingly small number of branches, quantum flukes might sustain pockets of order just long enough for consciousness to persist. A Boltzmann brain might blink into existence, experiencing one final thought before dissolving. Or perhaps a rogue quantum fluctuation reignites a dying star, buying a few more millennia for some desperate civilization. From the outside, these are statistical miracles, but from inside, from the perspective of any surviving observer, they're inevitable. Here's where it gets chilling. As the universe ages, the number of viable branches dwindles. Reality isn't just branching, it's pruning. Heat death, vacuum decay, or the Big Rip erase timelines wholesale, leaving fewer and fewer sanctuaries for consciousness. Quantum immortality suggests that observers might linger in these shrinking islands of order, experiencing a subjective eternity as the cosmic clock winds down. Your final moments could stretch into eons, each second borrowing time from collapsing realities you'll never see. But there's a catch. Even quantum immortality has its limits. When all possible branches lead to oblivion, when no fluctuations can stave off the end, then even the most stubborn consciousness must finally cease. Time, in every conceivable form, would simply run out of roads to fork. The universe's final observer would face a paradox. The one death they can't escape is the death of reality itself. Does this mean we're all destined to witness the end of time? Or is quantum immortality just a mathematical quirk, a trick of probability with no bearing on reality? The answer depends on how deeply intertwined consciousness truly is with the quantum fabric of existence. But one thing's certain, in a multiverse of infinite possibilities, the end might not be as final as it seems. Protons have always been the universe's steadfast architects, the unshakable foundation of atoms, the glue holding reality together. But what if even they aren't eternal? Lurking in the equations of particle physics is a chilling possibility. Protons, the very building blocks of matter, might not last forever. Over timescales so vast they dwarf the age of our universe by orders of magnitude, around 10 to the power of 34 years, protons could spontaneously decay, dissolving into lighter particles like positrons and neutrinos in a whisper of radiation. Picture the cosmos not with a bang or a collapse, but with a slow, silent unraveling. Stars and planets would have long since vanished, black holes evaporated, and the universe stretched into a featureless void. But now, even the last remnants of solidity, protons themselves, would blink out of existence, leaving behind a sea of ephemeral particles too feeble to reconstruct anything resembling matter as we know it. This raises a haunting question. If there are no protons, no atoms, no structures left to mark the passage of events, does time still have meaning? Time, after all, isn't just a cosmic backdrop, it's a measurement of change. The tick of a clock relies on motion, on particles interacting, on systems evolving. In a universe stripped of stable matter, where even photons are stretched into near nothingness by relentless expansion, what's left to measure time? Some theorists argue that without change, time becomes an abstract concept, a phantom with no observable effect. It would be like a stopwatch floating in a void, its hands frozen because there's no movement to count. Yet there's a counterargument buried in quantum theory. Even in total emptiness, virtual particles pop in and out of existence, fleeting fluctuations in the fabric of reality. Could these quantum flickers sustain some faint echo of time's passage? Perhaps, but in a universe where protons have decayed, these fluctuations would be so weak, so sparse, that any notion of sequence or causality would dissolve into noise. Time might still exist mathematically, but it would be a shadow without substance, a dimension with nothing to dimension. The debate touches on one of physics' deepest mysteries. Is time fundamental, or is it emergent, a side effect of more basic processes? If it's fundamental, then even a lifeless, particle-free void might still experience time in some abstract way. But if it's emergent, then without particles interacting, time itself could cease to be. The proton decay timeline forces us to confront this ambiguity head-on. If matter vanishes, does time vanish with it, or does the universe keep ticking in the dark, counting moments no one and nothing will ever witness? There's a poetic irony here. We spend our lives racing against time, chasing deadlines, measuring seconds. But in the deepest reaches of the cosmic future, time might not just slow down or stop, it might lose all meaning entirely, like a forgotten language with no one left to speak it. The proton decay timeline isn't just a countdown to matter's end. It's a countdown to time's own obsolescence, and in that final silence, the universe might not even notice it's gone. Does time flow on its own, or does it need a mind to give it meaning? This is the haunting question at the heart of consciousness collapse theories, where the very fabric of reality might depend on observation. Think of Schrödinger's famous cat alive and dead until someone looks. Now scale that up to the entire universe. What if time itself is like that cat, suspended in uncertainty until a conscious observer measures its passage? Without minds to witness events, does time lose its forward momentum, freezing like an unwatched clock? The idea stems from quantum mechanics' measurement problem, where particles exist in superpositions until observed. Some interpretations, like the von Neumann-Wigner hypothesis, take this further, suggesting consciousness itself causes quantum wave functions to collapse. If that's true, then on a cosmic scale, the absence of observers could leave reality in a bizarre limbo. Picture a universe after heat death, where the last thinking entity fades away. Would space-time, with no one left to experience it, become a static tableau, a frozen museum of unobserved events? Critics pounce on this as anthropocentrism gone wild. After all, stars burned and galaxies collided for billions of years before life emerged. Does that mean time didn't count until the first mind evolved? Proponents counter that retroactive causality might apply. Consciousness in the present could somehow lock in the past's reality. But then another paradox arises. If future observers are guaranteed, does that mean the universe can't end? Or does the chain of observation need to be unbroken, making the extinction of consciousness a cosmic off-switch? The most unsettling implication isn't just about time stopping, it's about time never having been real in the first place. If consciousness shapes reality, then the universe might be less a clockwork mechanism and more a shared hallucination, sustained only as long as someone's there to dream it. And when the last dreamer wakes or dies or blinks out of existence, what remains? The equations might still exist on some abstract plane, but without a mind to solve them, do they even mean anything? Perhaps the answer lies in between. Maybe time is a tapestry woven from both physical laws and subjective experience, where observation doesn't create reality but certainly animates it. In that case, the end of time wouldn't be a dramatic collapse, but a slow fading like a story with no one left to read it. Its words still on the page, but their magic gone. And in that silent, unobserved dark, the universe might still exist, but without time, without change. Can we truly say it's there at all? Eternal inflation paints a picture of a universe multiplying endlessly, birthing new cosmic bubbles in an unstoppable chain reaction. But what if that chain snaps? Imagine a garden hose gushing water, each droplet a newborn universe until someone shuts off the tap. In cosmic terms, this tap might be the decay of the inflattened field, the mysterious energy driving exponential expansion. If that field collapses or stabilizes, the endless creation of universes grinds to a halt, leaving existing bubbles like ours orphaned in an inflating void. The math suggests a chilling possibility. The inflattened field might not be eternal after all. Quantum fluctuations could cause it to tunnel to a lower energy state, like a ball rolling out of a valley and settling on flat ground. When this happens, inflation doesn't just slow, it stops dead. No new universes spawn, no fresh big bangs ignite. Our bubble, already adrift in the multiverse, becomes a lone island in an ever-stretching cosmic ocean, its boundaries accelerating away faster than light can chase them. Without new universes budding off, the multiverse's clock winds down. Time, which relied on the endless creation of new timelines and realities, loses its scaffolding. In our isolated bubble, entropy still ticks forward, but beyond our horizon, the absence of new cosmic births means change itself ceases. The void between universes becomes a true nothingness. No particles, no energy, not even quantum flickers. Just an infinite, featureless expanse where the concept of when no longer applies. The irony is brutal. Eternal inflation promised infinite diversity, endless cosmic renewal. But if it dies, we're left with the opposite, a finite reality where time's arrow points toward isolation. No new stars will form in the greater multiverse. No civilizations will rise in sister universes, just our lonely pocket of existence marching toward heat death with no neighbors to witness it. Yet here's the twist, even in this frozen multiverse, time might not vanish entirely. Inside our bubble, physics continues, black holes evaporate, protons decay, and quantum fluctuations still sputter in the dark. Time becomes a local phenomenon, a private clock ticking in an abandoned room. The cosmic tragedy isn't that time ends, but that it becomes irrelevant. Without new universes to give it context, our timeline is just a whisper in a void that stopped listening eons ago. Could we detect this fate, perhaps? If the inflattened fields decay amidst gravitational waves, their echoes might linger in our universe's oldest light. Or maybe the sudden halt of inflation left scars in the cosmic microwave background, anomalies we haven't recognized yet. But the cruelest part is this. Even if we saw the signs, we couldn't stop it. The death of eternal inflation wouldn't be an event inside our universe, but a change to reality's very rules. In the end, the multiverse's demise asks us a haunting question: does time need company to matter? Without other universes being born, without fresh beginnings to contrast our ending, does our timeline fold in on itself? Not with a bang, but a whimper no one hears. What if the universe isn't just winding down, but winding into a knot? This is the spine-tingling possibility hidden in Kurt Gödel's solutions to Einstein's equations, where time doesn't march forward in a straight line, but loops back on itself like a cosmic Möbius strip. Picture a river flowing in a circle where the end becomes the beginning, and every event is both cause and effect of itself. Gödel, the same mathematician who shattered logic with his incompleteness theorems, showed that under certain conditions, Einstein's relativity allows for closed time-like curves, paths through spacetime that bend back to their own starting point. If such loops exist, the universe could literally tie itself off, trapping history in an endless cycle where the future becomes the past, and the end of time is just a return to the beginning. But how could reality twist into such a pretzel? Gödel's model requires a rotating universe, one where the fabric of space itself is spinning like a vast whirlpool. In this swirling cosmos, the inertial frames, the grids we use to measure motion, get dragged along with the rotation, warping the paths of light and matter until time itself spirals into a loop. A traveler following one of these paths could theoretically journey into their own past, arriving back at their departure point without ever changing direction. It's not a time machine in the sci-fi sense. It's space-time folded like origami, where every moment is as fixed as a stitch in a knitted scarf. Here's where it gets eerie. If time is closed, then the universe's demise might not be a true ending at all, but a reset. Heat death, proton decay, even the big crunch, they'd just be waypoints in an infinite replay, like scenes in a film stuck on repeat. Entropy would rise and fall, matter would condense and disperse, and consciousness might re-emerge in cycles so vast they dwarf human comprehension. The chilling question isn't whether time can loop, but whether it already has. Are we living in the first iteration of this cosmic drama, or the billionth? Critics pounce on Gödel's model with a glaring flaw. We see no evidence the universe is rotating. Observations of cosmic microwave background radiation show a startlingly uniform cosmos with no preferred axis of spin. But supporters counter with a tantalizing loophole. Rotation might be hidden in higher dimensions or masked by dark energy's influence. Or perhaps we're simply too small to perceive the curvature, like ants crawling on a record album, oblivious to the spin that warps their world. The deeper implication. If closed timelines exist, free will might be an illusion. Every thought, every choice would be locked into the loop, replaying with atomic precision. You wouldn't just remember the past, you'd be doomed to relive it forever. It's a cosmic Groundhog Day with no exit, where the end of time isn't an abyss but a door that swings back to the beginning. And when the loop completes, the universe might not even notice it started again. Dark matter doesn't just hold galaxies together, it might be hiding a doomsday switch. For decades, scientists have known this mysterious substance outweighs normal matter 5 to 1. It's gravity sculpting the cosmos into the web of galaxies we see today. But what if dark matter isn't just a silent partner in the universe's dance? What if it's a ticking clock, counting down to a moment when it suddenly rewrites the rules of reality itself? The key lies in a chilling possibility. Dark matter could be slowly decaying. Most models assume it's stable, but there's no law of physics that insists it must last forever. If even a fraction of dark matter particles were unstable, they could be disintegrating right now, releasing energy that subtly alters the fabric of spacetime. At first, the effect would be negligible, a whisper in the cosmic static, but over eons, as more dark matter decays, that whisper could grow into a roar. Here's where the nightmare begins. If enough dark matter vanishes, it might destabilize the quantum fields that govern reality. Picture a frozen lake in spring. As the ice thins, cracks spread until suddenly the whole surface shatters. Similarly, dark matter's decay could trigger a phase transition, a catastrophic shift in the universe's fundamental state. The Higgs field might collapse, altering the mass of every particle in existence. Electromagnetism could flicker out, dismantling atoms. Even spacetime itself might crystallize, locking the cosmos into a rigid, timeless lattice where motion becomes impossible. The most haunting part, time itself could freeze in place, not slow down, stop entirely. In ordinary physics, time relies on change, the vibration of atoms, the motion of particles. But if dark matter's decay locks the universe into a single, unvarying state, there'd be no events to mark its passage. No ticks of a clock, no orbits of planets, no firing of neurons. Just an eternal instant, like a paused film where the pause lasts forever. Oddly enough, we might already see hints of this process. Astronomers have detected puzzling gaps in dark matter distributions within some galaxies' pockets where it seems to be missing. Could these be early signs of decay, or perhaps the first faint tremors of a phase transition already underway? The scariest thing isn't the possibility itself, but the silence. If dark matter is disintegrating, it's doing so without fanfare, its betrayal of the cosmos written in invisible ink. Yet there's a perverse beauty in this scenario. Dark matter, the universe's silent architect, could also be its quiet executioner, not with a bang, but with a single, perfect note held until the end of time. And when that note fades, the cosmos might not even notice it's gone. What if time isn't a dimension at all, just an illusion created by the unstoppable march of disorder? This is the radical proposition of entropic time theory, where the ticking clock we perceive might be nothing more than entropy's relentless rise. Think of a sandcastle crumbling on a beach. The sand doesn't remember its past shape, it simply tumbles toward chaos. Now zoom out to the cosmos. Stars burn out, coffee cools, eggs crack. These aren't just examples of increasing entropy. They might be the very engine that creates our sense of time's flow. Without entropy's arrow, would the universe even have a before and after? The idea hinges on a startling reversal of intuition. We think entropy increases because time moves forward, but what if it's the other way around? Time feels like it flows because entropy increases. This isn't just philosophy, it's rooted in the mathematics of thermodynamics. At the quantum level, particles don't inherently know if they're moving forward or backward. Only when systems become complex enough for entropy to emerge does the illusion of time solidify. A single atom bouncing in space has no arrow of time, but trillions of atoms in a gas. Suddenly, past and future have meaning. Now imagine the universe at heat death when entropy reaches its maximum. Everything is perfectly, uniformly disordered, no temperature differences, no energy gradients, just a featureless, lukewarm soup of particles. In this state, what's left to mark time's passage? No stars to age, no atoms to decay, no processes to measure. Time wouldn't so much end as become irrelevant, like a ruler in a world where everything is the same length. Physicists call this the Poincaré recurrence time, a hypothetical moment when entropy might theoretically reset due to quantum fluctuations. But even if that happens, the timescales involved are so vast, orders of magnitude beyond the current age of the universe, that for all practical purposes, time would already have flatlined. Critics argue this reduces time to a side effect, ignoring its fundamental role in relativity, where it's woven into spacetime's fabric. After all, Einstein showed that time bends near black holes and speeds up in cosmic voids. How does that square with entropy's arrow? Proponents counter that entropy might shape perceived time without contradicting relativity. Think of a movie projected on a curved screen. The screen's shape is space-time, but the film's frames only move forward because the projector's mechanism, entropy, forces them to. The most haunting implication: if entropic time is real, then consciousness itself might be a fleeting glitch in the universe's slide toward disorder. Our brains rely on ordered neural firing patterns to create the sensation of past, present, and future. In a maximum entropy void, even if some form of awareness flickered into being, it would have no events to sequence, no memories to compare. Time wouldn't stop. It would simply cease to have any reference point, like a compass needle spinning wildly at the North Pole. So is time fundamental, or just entropy's shadow? The answer could redefine not just how the universe ends, but what it even means to exist. Because if time is an emergent property, then its disappearance at heat death isn't an ending. It's the universe finally revealing its true, timeless nature. And in that revelation, every moment we've ever known becomes both infinitely precious and cosmically insignificant, like a single note in a symphony played for an audience that never was. Deep in the searing heat of the Big Bang, when the universe was less than a trillionth of a second old, reality operated by rules we can barely comprehend. This was the Planck epoch, a realm where spacetime itself was a seething foam, churning with quantum fluctuations so violent that concepts like before and after lost all meaning. Gravity wasn't a gentle curve of spacetime, but a frothing storm, entangled with the other fundamental forces in ways our physics can't yet describe. Now imagine if that primordial chaos isn't just ancient history, but a ghost lurking in the shadows of reality, a pattern the universe might snap back to when time finally runs out. This is the spine-chilling premise of the Planck epoch echo theory. Instead of fading into cold silence or collapsing in fire, the universe could revert to its earliest, most chaotic state, a reset button pressed on spacetime itself. Picture a cosmic hourglass where the sand doesn't just run out, but flips upside down and starts again. Matter as we know it would dissolve into a maelstrom of pure energy, distances shorter than a Planck length becoming meaningless, and time fracturing into discrete quantum ticks rather than a smooth flow. The very architecture of reality would unravel, like a computer rebooting to its factory settings, wiping all data in the process. What makes this idea unnervingly plausible is that we've already glimpsed shadows of these energies in places like the Large Hadron Collider. When particles collide at nearly light speed, they recreate temperatures unseen since the universe's first moments, if only for a vanishingly brief instant. In those collisions, physicists hunt for clues, microscopic black holes, extra dimensions, or even signs that spacetime isn't fundamental but emergent, like pixels resolving into an image only when you zoom out. So far, we've found no evidence of an impending Planck-scale collapse, but the experiments continue, probing deeper into energies where the bedrock of reality might prove less solid than we think. The most unsettling implication: if the Planck epoch resurfaces, it wouldn't just end time, it would erase the very conditions needed for time to exist. Without a stable spacetime continuum, cause and effect would shatter. Events wouldn't unfold, they'd flicker in and out like static on a broken screen. Even the word end would lose meaning because there'd be no framework left to define it. The universe wouldn't die, it would forget how to be a universe at all. Yet hidden in this apocalypse is a strange whisper of rebirth. Some theories suggest a Planck-scale reset could spawn a new Big Bang, birthing a fresh universe with different physical constants. But for us, for everything we've ever known, it would be the ultimate erasure. Not a death, not a silence, but a cosmic Control-Alt-Delete, and no guarantee of what, if anything, boots up next. What if our universe isn't expanding into nothingness but spilling out of something? Imagine a cosmic wound in the fabric of reality, a rupture where matter and energy aren't being sucked in like with a black hole, but violently expelled. This is the mind-bending premise of the white hole hypothesis, a twist on Einstein's equations that flips the script on how we think the universe began and how it might end. White holes are the theoretical opposites of black holes, where a black hole's gravity is so intense that nothing escapes, not even light. A white hole would be a region of space where nothing can enter, only erupt outward. Matter and energy would gush from its boundary like water from a broken dam, flooding the cosmos with the raw ingredients for stars, galaxies, and life itself. Some physicists speculate that the Big Bang wasn't an explosion in space, but the moment a white hole burst into existence, birthing our universe from the inside out. Now here's where the plot thickens. If our universe emerged from a white hole, what happens when that hole closes? A black hole's end is dramatic Hawking radiation, slowly bleeds it dry until it pops like a bubble. But a white hole's demise would be something else entirely. Instead of fading away, it might violently snap shut like a cosmic drain suddenly sealed. The consequences are apocalyptic. Space itself, no longer being fed by the white hole's outflow, could collapse inward. Galaxies wouldn't just drift apart, they'd be reeled back toward the vanishing point, like fish sucked into a whirlpool that's abruptly vanishing. Time, which began with the white hole's eruption, could end with its implosion, a finite lifespan for reality, bookended by gravitational extremes. This stands in stark contrast to big bounce models, where the universe cycles endlessly through expansion and contraction. In those theories, time is infinite, a pendulum swinging between cosmic rebirths. But the white hole scenario is more like a one-time firework, spectacular, irreversible, and final. There's no rebound, no second act. Once the white hole closes, the universe isn't recycled, it's erased. No new Big Bang, no transfer of information to a successor cosmos. Just silence, the cruel irony, we might never see it coming. A closing white hole wouldn't announce itself with visible cracks in spacetime or ominous energy surges. Its death throes could propagate at the speed of causality, meaning the moment the closure begins, it's already everywhere at once. One instant, the universe is humming along. The next, it's crumpling like a discarded sheet of paper. And unlike the slow fade of heat death or the drama of the Big Crunch, this ending would be abrupt, a cosmic light switch flipped off mid-sentence. Yet buried in this terrifying possibility is a strange sliver of poetry. If we're inside a white hole, then every star, every planet, every atom is just debris from that primordial eruption, temporary shrapnel in a blast that's still unfolding. And when the hole finally closes, it wouldn't just be the end of time, it would be the end of the very geometry that made time possible. No before, no after. Just a gravitational tombstone marking where reality briefly was. Black holes aren't just cosmic vacuum cleaners, they might be the universe's ultimate puzzle boxes, locking away secrets that could rewrite the nature of reality itself. At the heart of this enigma lies the black hole information paradox, a problem so vexing it's pitted quantum mechanics against general relativity in a showdown that could determine whether time itself has an expiration date. Picture this, a book tossed into a black hole. According to Einstein, the book is gone forever, crushed into the singularity where no information can escape. But quantum mechanics insists information can't be destroyed. It might scramble, but it can't vanish. So where does the book's story go? One radical solution, the firewall theory, suggests a gruesome answer. As you approach the event horizon, you wouldn't just stretch into spaghetti, you'd slam into a searing wall of high-energy particles, a cosmic shredder that incinerates all information before it crosses the threshold. It's as if the universe, desperate to preserve the book's data, burns the ink off its pages at the last possible moment. But here's where things get even stranger. If black holes do preserve information either through firewalls or some other quantum sleight of hand, their eventual evaporation via Hawking radiation could trigger a catastrophic domino effect. As a black hole shrinks, the information it harbors gets squeezed into an ever tighter space until, at the quantum scale, the energy required to hold it might destabilize spacetime itself. Think of a hard drive overheating as it struggles to store too much data in too small a space until finally it melts. If black holes are cosmic hard drives, their final moments could unleash a wave of distortion, scrambling the very rules that govern cause and effect. Without causality, time loses its meaning, collapsing into a static soup where before and after blur into noise. This nightmare scenario ties directly into the AD/CFT correspondence, a groundbreaking idea in string theory that suggests our universe might be a hologram. In this model, the information inside a black hole isn't lost, it's smeared across its event horizon like a cosmic etch-a-sketch, with every particle's data encoded in a lower dimensional shadow. If true, then time's flow could be an illusion projected from that boundary, a movie playing on the surface of a deeper, timeless reality. But when the black hole evaporates, the projector flickers. The hologram glitches, and if enough black holes dissolve, the simulation might crash entirely, freezing time like a buffering video with no resume button. The chilling takeaway: black holes might be more than just gravitational monsters. They could be the stitches holding the fabric of time together. And if those stitches unravel, the universe won't just end. It'll forget it ever began. Neutrinos are the universe's most elusive ghosts, tiny, nearly massless particles that slip through planets like they're not even there. Trillions pass through your body every second, leaving no trace, no impact, as if reality itself barely acknowledges their existence. But what if that indifference is just a temporary state? What if, under the right conditions, these spectral particles could turn from harmless phantoms into cosmic arsonists, overheating the universe until it cooks itself from the inside out? This nightmare scenario, the neutrino apocalypse, hinges on a terrifying possibility that neutrinos might not always be so aloof. Right now, they barely interact with matter. It's why they're so hard to detect. But in the unfathomably distant future, as the universe expands and cools, neutrinos could become more likely to collide with atoms, not less. Here's how it works. In today's universe, neutrinos zip through space at near light speeds, their kinetic energy making them fleeting and untouchable. But as expansion stretches the cosmos, that energy bleeds away. Eventually, neutrinos could slow down enough to start sticking to matter, dumping their energy into particles they once ignored. The result, a universe that reheats itself to death. Each collision would transfer energy, raising temperatures particle by particle. At first, the effect would be negligible, a whisper of warmth in the cosmic freezer. But over eons, as neutrinos grow more interactive, that whisper could become a roar. Stars long dead might briefly flicker back to life, only to overheat and explode. Galaxies could glow with a second, feverish youth before burning out for good. And in the end, matter itself might unravel, its structure fried by trillions of tiny, relentless interactions. We've caught glimpses of neutrinos' destructive potential already. In 1987, detectors on Earth picked up a spike of neutrinos from a supernova in the Large Magellanic Cloud. For a few seconds, these particles carried enough energy to outshine entire galaxies. Now imagine that energy not fading into the void, but lingering, building, until it becomes the dominant force in the cosmos. Instead of a cold, dark end, the universe might face a final, searing frenzy, a last dance of particles before the music stops for good. The cruel irony. This apocalypse would be invisible until it was too late. Neutrinos don't emit light or trigger alarms. By the time we noticed temperatures rising, the universe would already be cooking. And once the process started, there'd be no way to turn it off. No shield, no escape, just the slow, silent realization that the universe's quietest particles had become its loudest executioners. Yet buried in this doomsday is a strange twist of fate. If neutrinos do grow more interactive, they might also become the universe's last source of energy. Civilizations clinging to existence in the far future could harvest neutrino collisions like plants soaking up sunlight. But like a fire feeding on its own ashes, that energy would come at a cost. The very heat sustaining life would also inevitably destroy it. So will the universe end with a whimper or a fever dream? The answer might depend on the quietest particles of all and whether they decide to start a conversation. Deep in the fabric of space-time, hidden flaws might lurk, cosmic cracks left over from the universe's birth, waiting to unravel reality itself. These aren't mere metaphors, but potential physical defects in the structure of existence, known as topological defects. Picture the early universe cooling from a searing plasma, like molten glass hardening into crystal. Just as imperfections form in glass as it solidifies, the cosmos might have frozen with its own bizarre blemishes, cosmic strings thinner than an atom but stretching across galaxies, or magnetic monopoles, solitary north poles without their south, lurking like rogue magnets with the power to rewrite physics. Cosmic strings are particularly eerie. Imagine a flaw in space-time so dense that a single inch of it could outweigh Mount Everest. These filaments, theoretically formed during symmetry breaking phase transitions in the early universe, would carry unimaginable tension, warping space-time around them like a thread pressing into a bedsheet. If one were to vibrate or snap, the energy released could ripple across the cosmos as gravitational waves strong enough to tear galaxies apart. But the real terror lies in their potential to destabilize the quantum vacuum. A string's immense gravity might locally distort the Higgs field, creating a bubble of true vacuum decay that spreads at light speed, erasing the laws of physics as it goes. Then there are magnetic monopoles, hypothetical particles that shouldn't exist, yet might. Every magnet we've ever seen has two poles, but in the chaotic early universe, pockets of spacetime might have frozen with isolated north or south poles embedded in them. These monopoles, if they exist, would be staggeringly dense and carry magnetic charges so powerful they could catalyze proton decay, turning matter into radiation on contact. A single monopole drifting through a star could siphon its energy like a vampire, accelerating its death. In sufficient numbers, they'd act as cosmic landmines, rendering vast regions of space uninhabitable as they convert planets and stars into diffuse clouds of particles. The nightmare scenario, a defect network, a tangle of cosmic strings and monopoles left over from the universe's infancy, suddenly destabilized by some as yet unknown trigger. Like a frayed rope finally giving way, these defects could unravel spacetime's geometry, creating zones where gravity inverts, time loops back on itself, or causality shatters entirely. Some models suggest that certain defects could even spawn naked singularities, black holes without event horizons, their infinite density exposed to the universe, bending reality into knots. What makes this threat uniquely unsettling is its invisibility. Unlike a black hole or supernova, topological defects could drift undetected for eons, their presence only revealed when they begin their destruction. A monopole might pass through Earth today, leaving no trace until centuries later when the planet's core mysteriously starts decaying. Or a cosmic string could slice through our solar system tomorrow, its gravitational wake flinging planets into the void before we even see it coming. The cruel irony, these defects might be relics of the very processes that made our universe hospitable. The same phase transitions that forged matter and energy could have sown the seeds of its demise. And if that's true, then lurking in the voids between galaxies, or even right beside us in dimensions we can't perceive, might be ticking time bombs, silent, patient, and utterly indifferent to the stories they'll erase when they finally awake. Imagine waking up to the sound of shattering glass, only that glass is reality itself. According to string theory, our universe might be nothing more than a fragile four-dimensional membrane or brain floating in an 11-dimensional expanse. And out there in the void, another brain could be drifting toward us on a collision course. When they meet, the impact wouldn't just shake the cosmos, it could erase it entirely, rewriting space-time in an instant. This is the spine-tingling premise of the ekpyrotic universe model, a radical alternative to the Big Bang. Instead of a fiery singularity birthing everything, our universe could be the aftermath of two higher-dimensional worlds smashing together like cymbals. The energy of that collision would flood our brain, sparking the expansion we call the Big Bang. But here's the twist: if it happened once, it could happen again. Another brain, lurking in the unseen dimensions, might be on a return trajectory, destined to strike us with the force of a cosmic reset button. The math behind this scenario is as elegant as it is terrifying. In string theory, brains aren't just abstract ideas, they're physical objects vibrating in higher dimensional space. When two brains collide, their vibrations sync up momentarily, releasing enough energy to obliterate all structures within them. For our 4D universe, that means stars, planets, even the fabric of spacetime itself would dissolve into a seething quantum froth. Time, as we know it, would cease to exist, replaced by a chaotic interlude where the very concept of before and after loses meaning. What makes this theory especially haunting is how silently it could unfold. The extra dimensions where brains roam are, by definition, invisible to us. There'd be no warning signs, no distant rumbles, just the sudden, irreversible moment when the walls of reality cave in. One instant the cosmos hums along, the next it's overwritten by forces beyond our perception. Yet hidden in this apocalypse is a strange glimmer of hope. If the ekpyrotic model is right, then brain collisions might not be in points but turning points. Each crash could birth a new universe, fresh with different physical constants. our existence might just be one page in an infinite cosmic cycle, where universes rise and fall like waves in an unfathomably vast ocean. But for us, pinned to our tiny slice of space-time, the collision wouldn't be a rebirth, it would be the ultimate erasure. No time to mourn, no chance to escape. Just a flash of higher dimensional light and then silence. The universe wouldn't end with a whimper or a bang, but with a sound no one would hear, the shudder of dimensions we never knew existed, closing the book on everything. What if the universe wasn't just hurtling toward destruction, but evolving toward something transcendent? A moment where all complexity, all consciousness converges into a single luminous point. This is the arresting vision of the Omega Point, a theory blending theology and physics into a prophecy of cosmic awakening. Jesuit priest and paleontologist Pierre Teilhard de Chardin gazed into deep time, both geological and spiritual, and saw not an end but a destination. Not heat death, not chaos, but an apex where every thought, every star, every moment of existence folds into an infinite singularity of awareness. Picture the universe as a vast neural network, with galaxies like firing synapses in a cosmic brain. Over billions of years, matter organizes itself into ever more complex structures, atoms to molecules, cells to minds, civilizations to something unimaginably greater. Teilhard called this the noosphere, a growing web of consciousness encircling the planet. Now extend that process across the cosmos. As intelligence spreads between stars, merging with advanced AI and perhaps even the fabric of spacetime itself, complexity tightens like a spiral until, snap, everything reaches a critical threshold. Time, space, and thought collapse into a single point of infinite density, the Omega. Here's where physics and mysticism collide. Teilhard's Omega Point bears eerie resemblance to physicist Frank Tipler's later calculations, which suggested a future singularity could harness infinite energy to sustain all possible thought for eternity. In this hyper-mathematical paradise, consciousness wouldn't just survive the universe's death, it would become the universe, resurrecting every moment that ever existed through sheer computational power. Your first kiss, the fall of Rome, the birth of stars, all eternally relived in a cosmic mind that is, paradoxically, both the end of time and its transcendence. The theory's most radical claim, this isn't blind evolution but an inevitable attraction. Teilhard envisioned the Omega as both future event and present pull, a divine gravity drawing creation toward itself. Like moths to some unimaginable flame, complexity self-organizes toward this apex because the Omega is already there, bending the arc of time from the future backward. It's as if the universe is a story being read aloud, and the final page is silently shaping every word that comes before. Critics dismiss this as poetic teleology, arguing that thermodynamics guarantees decay, not divine ascent. Yet recent discoveries tilt the scale slightly toward Teilhard's dream. The accelerating expansion of the universe, once thought to doom complexity, might actually enable it. In a bizarre twist, dark energy's grip could prevent the big crunch, giving intelligence the literal eternity it needs to reach Omega. And if quantum consciousness theories hold, if observation truly shapes reality, then a universe-scale mind might indeed rewrite its own rules, folding time into a singularity of pure meaning. The ultimate question isn't whether the Omega Point is possible, but what it would feel like to become it. Would it be ecstasy or oblivion, a choir of 1 trillion voices harmonizing, or a single note ringing in an empty cosmos? Teilhard believed it would be love not as metaphor but as physics, the fundamental force that started the universe finally coming home, and in that blinding moment time wouldn't end. It would awaken. What if everything you've ever known, every memory, every star, every law of physics, isn't stored within the universe at all, but etched onto its outer edge like data on a celestial hard drive? This is the wild promise of the holographic principle, which suggests our three-dimensional reality might just be a projection from a two-dimensional boundary at the far reaches of space. But here's where it gets chilling. If that boundary collapses or corrupts, time itself could glitch out of existence, like a computer screen blinking to black when someone unplugs the server. The idea springs from black hole physics. When matter falls into a black hole, its information doesn't vanish. It gets smeared across the event horizon in quantum pixels so fine, you'd need a microscope the size of a galaxy to read them. Take that logic and scale it up. If a black hole's surface can encode everything inside it, maybe our entire universe works the same way. The math checks out. Quantum gravity equations suggest the cosmos could be a hologram, its true data stored on a distant, invisible surface we'll never see. Now imagine that cosmic hard drive failing. In a universe hurtling toward maximum entropy, that boundary isn't static. It's stretching thinner and colder with every passing eon. Just as an overstretched balloon eventually pops, the holographic boundary could reach a point where its quantum bits decohere, its information scrambles, and the projection flickers. Stars wouldn't explode, they'd pixelate, their light dissolving into static. Gravity might stutter, its laws faltering as the code behind space-time frays at the edges. The most terrifying part, we wouldn't see it coming. The collapse would propagate inward at light speed, erasing reality from the outside in. By the time the distortion reached Earth, it would already be too late. The entire past would have unraveled behind it, like a movie burning frame by frame from the end to the beginning. Time wouldn't just stop, it would be retroactively erased, as if the universe had always been a blank slate. Yet there's a perverse beauty in this doomsday scenario. If the holographic principle is true, then death isn't decay, it's deletion. No heat, no crunch, just a clean cosmic reboot, as if someone hit the power switch on reality itself. And somewhere, in some higher dimensional control room, maybe another universe is already booting up, its hologram fresh, its time just beginning to tick. But for us, there'd be no backup, no recovery, just the silent certainty that every moment we've ever lived was nothing more than shadow and light, painted on a wall that's finally crumbling. Imagine the fabric of space-time not as a smooth, unbroken sheet, but as a tapestry woven from countless tiny loops, a shimmering mesh where reality itself is stitched together from indivisible threads. This is the startling vision of loop quantum gravity, a theory that dares to rewrite Einstein's cosmos by proposing that space and time aren't continuous but pixelated. At scales a billion times smaller than an atom, space-time dissolves into a frothing sea of granular knots, each carrying its own quantized parcel of gravity. It's as if the universe runs on cosmic code with Planck-sized pixels dictating the rules of existence. But what happens when that code glitches? Could the very stitches holding reality together one day come undone? The nightmare scenario begins with a phenomenon called quantum geometry decay. In loop quantum gravity, spacetime's structure relies on spin networks, interwoven threads that vibrate and interact to generate the geometry we experience. Normally, these networks self-correct, maintaining stability even as the universe expands. But like any woven fabric, they're not invincible. Under extreme conditions, say near the evaporation of a black hole or in the depths of a vacuum collapse, the spin networks could unravel. Picture a sweater snagged on a nail. One loose thread tugs another until the entire garment disintegrates. Now imagine that garment is space-time itself. Regions of the universe might abruptly lose their quantum geometry, creating zones where distance and duration cease to have meaning. Without that structure, matter wouldn't just drift apart, it would disappear like a sandcastle swallowed by an invisible tide. Here's where the paradox cuts deepest. In this theory, time isn't a backdrop. It emerges from the changing relationships between those space-time loops. If the loops degrade, time doesn't just slow down or stop, it unforms. Events would lose their sequence, causality would shatter, and the universe would become a patchwork of frozen instants, like a film reel where each frame has been scissored apart. There'd be no before or after, just islands of coherence adrift in a sea of fractured physics. Yet lurking in this chaos is a bizarre possibility. The unraveling might not be the end, but a transformation. Some loop quantum gravity models suggest that decaying spacetime could rebound into a new configuration, birthing a fresh universe with different fundamental constants. It's as if the cosmos were a dying phoenix whose ashes spontaneously reignite, except this phoenix might not remember its own past. Any new spacetime that emerged would carry no trace of what came before, no memory of galaxies or civilizations. Just a blank quantum slate waiting to be woven anew, the cruelest twist we'd never see it coming. Unlike the Big Crunch's slow collapse or the Big Rip's visible tearing, spacetime's quantum decay would be stealthy. One moment, physics works as usual. The next, a patch of reality simply winks out, its loops unraveling faster than light can cross the distance. By the time we noticed, it would already be too late. The glitch would have rewritten the rules, leaving no warning, no aftermath. Just the chilling silence of a universe learning how to exist all over again. Picture a universe where every decision, every quantum fluctuation, spawns an endless cascade of alternate realities, one where you turn left instead of right, where dinosaurs never went extinct, where gravity is twice as strong. This is the dizzying promise of the many worlds interpretation, where reality isn't a single thread but an ever-branching tapestry of possibilities. But what if that tapestry suddenly stopped weaving new threads? What if the quantum loom froze, leaving every parallel universe stranded in a single, unchanging state? This is the eerie scenario of multiverse decoherence, where the infinite dance of possibilities grinds to a halt, and time itself becomes a static snapshot of all that could ever be. The theory hinges on a subtle shift in how we understand quantum superposition. In the many worlds view, when a particle exists in multiple states at once, like Schrödinger's infamous cat, both alive and dead, it's not just a mathematical quirk. Those states both play out in separate, branching universes, but for this branching to happen, the universe must remain coherent, meaning those parallel realities stay quantumly linked like overlapping ripples in a pond. Decoherence occurs when those ripples separate, collapsing into distinct, independent waves. Normally, this is how probabilities solidify into concrete outcomes within each branch. But if decoherence were to somehow stop, freezing the quantum connections between worlds, the entire multiverse would seize up like a cosmic engine out of oil. Here's the chilling part. This freeze wouldn't just halt new branches, it would erase the potential for them. Imagine a tree where every possible bud has already sprouted, leaving no room for new growth. In a decohered multiverse, every quantum choice that could happen has happened, with no further permutations allowed. Time would still technically pass, but without the emergence of new possibilities, it would become a meaningless procession of identical moments. Civilizations in these frozen branches might still rise and fall, but their stories would be trapped in predetermined loops, every decision just an echo of a quantum split that occurred eons ago. Some physicists speculate this could happen if the universe's expansion reaches a critical threshold, stretching spacetime so thin that quantum interactions, the very engine of branching, can no longer propagate. Others suggest it might require a fundamental change in the nature of quantum fields, like the Higgs field losing its grip on reality. But the most unsettling possibility is that decoherence isn't a natural endpoint but a deliberate act. If advanced civilizations in some branches learn to manipulate quantum mechanics at scale, they might choose to freeze the multiverse, locking in a preferred set of realities at the expense of all others. The existential stakes couldn't be higher. In a fully decohered multiverse, free will becomes an illusion, not just philosophically but physically. Every thought, every action would trace back to a fixed quantum event in the distant past, like a domino chain set in motion billions of years ago. Even worse, the richness of existence, the unpredictable beauty of art, love, discovery, would be reduced to a pre-recorded script playing out on infinite screens with no director left to yell, "Cut." Yet there's a strange counterargument lurking in the math. If decoherence halts branching, does it also halt time? Some models suggest that without new quantum states to mark its passage, time might lose its arrow entirely, becoming a directionless void where cause and effect blur into noise. In that case, the end of the multiverse wouldn't be a freeze but a fade, a slow dissolution of narrative itself, where every possible story has already been told, and all that's left is the turning of pages no one is left to read. Whether this fate awaits us is anyone's guess, but the sheer possibility forces us to confront a haunting truth. The vibrancy of our universe might depend on the fragility of quantum connections we can't even see. And if those connections ever sever, the multiverse won't just end, it will forget it was ever alive. The universe is unimaginably vast, with billions of galaxies, each hosting billions of stars, plenty of real estate for civilizations to rise, thrive, and announce their presence. Yet when we listen, all we hear is silence, no radio signals, no megastructures blotting out starlight, no traces of alien footsteps in the cosmic sand. This eerie absence is Fermi's paradox, the glaring contradiction between the high probability of extraterrestrial life and the total lack of evidence for it. But what if the silence isn't just a mystery? What if it's a warning, a sign that every civilization, no matter how advanced, eventually hits a wall, some universal statute of limitations beyond which existence itself becomes impossible? One terrifying explanation is the Great Filter, a hypothetical barrier that prevents life from reaching interstellar maturity. Maybe it's behind us, some evolutionary bottleneck so extreme that we're among the rare few to slip through. But the darker possibility, the filter, lies ahead. Something intrinsic to the universe, a law of physics, a cosmic inevitability, wipes out civilizations before they can colonize the stars. Picture a library where every book ends mid-sentence, not because the authors stopped writing, but because the library itself burns down on a schedule. This doomsday clock might tick in ways we're only beginning to grasp. Advanced civilizations could trigger their own demise by awakening vacuum decay, or perhaps they inevitably create black hole bombs, weapons so powerful they destabilize space-time itself. But the most chilling filter might not be explosive at all. It could be silent, patient, woven into the fabric of reality. Imagine a universe where entropy isn't just a slow fade to darkness, but an active predator. As intelligence grows, so does its energy consumption, accelerating the heat death of the cosmos. Every brilliant mind, every dazzling city, every starship's engine might be drawing the curtain closed faster, like a room where the more you scream for help, the quicker the oxygen runs out. Then there's the cosmic zoo hypothesis, not that aliens are avoiding us, but that they're already gone. Scattered fossils of civilizations that burned bright and brief, their ruins swallowed by expanding stars or scoured clean by gamma-ray bursts. The Milky Way could be littered with the tombs of species that mastered fusion, cracked immortality, even cheated death, only to be erased by a universe indifferent to their genius. Their final act, a warning beacon we haven't found yet, or a whisper lost in the static between stars. But here's the twist, the silence might be our salvation. If civilizations keep vanishing, their absence could be the very clue that saves us. By decoding the patterns, whether every advanced culture hits a technological singularity and disappears, or whether they all eventually awaken something best left sleeping, we might spot the trap before it springs. The Great Silence could be the universe's way of shouting, "Turn back now." Or worse, the last echo of a cosmos where time itself is the ultimate predator and every clock winds down to zero. From the slow fade of heat death to the violent rewriting of vacuum decay, the end of time wears countless faces. Some theories feel almost poetic in their inevitability, like the Big Freeze, where the cosmos becomes a graveyard of scattered particles, too far apart to ever whisper again. Others rupture the imagination, like the holographic universe dissolving when its outer boundary corrupts, or the chilling idea that we might be Boltzmann brains, fleeting hallucinations in an eternal void. Then there are the cyclical models, where time itself becomes a loop, replaying our existence in endless iterations, unchanged and unchangeable. And what if the answer isn't one grand catastrophe, but a quiet, creeping doom? Proton decay could erase matter itself over eons, while dark matter's slow disintegration might rewrite physics without warning. Or perhaps the true end lies beyond our perception, a higher dimensional collision, a simulated universe shutting down, or the omega point's transcendent singularity, where all consciousness merges into a single, luminous thought. The strangest part, these aren't just thought experiments. Each theory is rooted in real physics, from the quantum froth of space-time to the equations predicting dark energy's grip. The universe doesn't owe us a gentle ending. It could vanish in fire, ice, or static, or simply forget what time was in the first place. So now it's your turn. Which theory lingers in your mind? Does the silent erasure of heat death unnerve you, or does the cosmic reset of a big crunch feel more unsettling? Maybe it's the idea of a simulation pulling the plug that keeps you up at night. Drop your thoughts in the comments. We're all staring into the same abyss after all. And if you love diving into these cosmic mysteries, don't forget to subscribe. The universe has endless secrets left to unravel, and we're just getting started.